I'm Abigail Lynch. I'm a grad student at Michigan State University, and on behalf of my co-author and advisor, Bill Taylor, I just wanted to thank the Commission for the opportunity to present. And I'm going to be presenting today on my dissertation research, which is looking at designing a climate change decision support tool for harvest management of Great Lakes whitefish. And in particular, my objectives for the talk today are to present preliminary results from a climate variable recruitment regression model that I'm developing and solicit feedback from you all in terms of recommendations for next steps with that, and also discuss a little bit about the next chapter of my dissertation looking at decision support. And I have a short survey that I'm going to distribute at the end if people are, I hope you will consider filling it out if you have an interest in lake whitefish management in the 1836 treaty waters. So just to go briefly through my outline for today, I'm going to start with a justification for this research, then go into the model that I'm developing for lake whitefish recruitment linked with climate variables, discuss some next steps for that model, and then lastly go into decision support and bring up the survey. So first question is why do we want to look at lake whitefish? This is probably not a very exciting question for you all because you all have reason to believe that whitefish are important, but again, just to reemphasize, they're an important food fish in the Great Lakes Basin. They have high commercial value. They're also a tribal staple. And lastly, they're an ecological pathway, being a benthic consumer and bringing energy through that pathway. Next, the question is why are we looking at climate in relation to lake whitefish? There have been a number of studies that have looked at climate variables and have found relationships between climate variables and lake whitefish recruitment. In particular, looking at water temperature, it's been linked with larval growth and survival. Ice cover has been linked with egg survival, particularly in suboptimal spawning habitats. So in years where there are high numbers of spawners and eggs are deposited in suboptimal habitat, ice cover has been shown to protect those eggs from effects from turbulence and storms. And so conversely, storm intensity has also been linked with survival of eggs, particularly again in years where there's large spawning biomass and eggs are deposited in suboptimal habitat. In that suboptimal habitat, they are exposed to potential impacts from wave and wind events. So, and then this begs the question, why look at climate change? And in the Great Lakes Basin, there's actually projected to be a greater volume of optimal thermal habitat for lake whitefish. And this may seem a bit counterintuitive when thinking about a cold water fish, and hopefully this simple schematic can help with that. If you consider each of these colors as a thermal band, and the depth on the y-axis here and the latitude being on the z-axis, if you have a fish that has an optimal thermal habitat within this light blue range, if the climate changes and the climate regime shifts, technically the fish could move deeper in the water column to maintain that same thermal habitat or move further north in the basin. But again, when you're thinking in terms of these projections, optimal thermal habitat projections are not necessarily the same as optimal realized habitat constraints. So in terms of ice cover, there's obviously expected to be significantly less ice cover in the lake, so that could have implications for survival of eggs over the winter, particularly again in terms of that suboptimal spawning habitat for years when there's high spawner biomass. But conversely, there's also expected to be a decline in average wind speeds. So maybe there's a potential confounding factor between those two. But again, you have to consider that a decline in average wind speed may not necessarily be the same, the best indicator for storm events in the future. So in terms of the objectives of my research project, the first thing is I'm looking to determine the relationship between climate variables, specifically these ones that have already been shown to have a relationship between lake whitefish recruitment, water temperature, ice cover, and storm intensity, and then from that relationship project the climate recruitment relationship with climate change. And then lastly, take that information and potentially design a decision support tool with managers and fishermen to inform harvest policy. So to kind of restate this in a more conceptual format, the idea is to link climate variables with the population dynamics of lake whitefish, which in addition to fishing pressure, determine the abundance and distribution of lake whitefish, which has an impact on management strategies, which in turn come back and influence fishing pressure. So in terms of my general approach, the first step is looking at verifying a climate recruitment relationship between for lake whitefish. And to do that, I'm looking at long-term trends in data, again, for these same three biologically relevant climate variables: water temperature, ice cover, and storm intensity. And some, but not all of this data, well, all of my data is publicly available, are publicly available, and a lot of it has come through the Great Lakes GIS project. And in terms of linking that to recruitment, I'm looking at a linearized Ricker stock recruitment model for the 1836 treaty waters, which are here shown on the map of Huron, Michigan, and Superior. And again, the 1836 treaty waters are the areas that were ceded by the tribes to the state of Michigan and in 1836, and have since, the tribes have since reasserted their rights to commercially fish in that area. And in the 1836 treaty waters, they have a statistical catch-at-age model that has been developed for each of the management units, well, for 13 of the management units, and actually Northern Lake Huron, the units are combined. And this is an extensive data set that has some management units having recruitment and stock estimates all the way back to 1976. So in terms of the model inputs for my regression model, the first one I'm looking at is ice cover, and for that I'm looking at the proportion of ice cover per management unit in mid-December, which is what I'm indicating as the end of the spawning season. For water temperature, I'm looking at mean monthly surface temperature in December and March as indicators of the end of the spawning season and the beginning of the hatching season. And I'm also looking at air temperature for the same two time periods, looking at temperature stations that are located within 5 miles of the management unit, the edge of the management unit. And then, as I mentioned previously, I'm getting spawning stock biomass and recruitment from these 13 statistical catch-at-age models. And again, those are the ones listed in blue. The units listed in gray don't have statistical catch-at-age models. So before I go into my equation slide, I just wanted to throw up this caveat that all models are wrong, but some are useful. And I've started thinking of an analogy of considering going to the eye doctor. When you're at the eye doctor, your objective is to see 20/20. And so the idea is to try and get an estimate of recruitment, but most of the time it's quite blurry. And so the idea of using a model in this context is to try the same way that an eye doctor will adjust your prescription. The idea of using a model is to use explanatory variables to try and get a slightly better, more clear picture of what recruitment is. So in terms of my regression model, that I start with a linearized Ricker stock recruitment model for lake whitefish, which have been shown to be density dependent. So stock recruitment is shown to be density dependent on stock size. So I'm also adding ice cover as a density dependent factor because, as I mentioned earlier, ice cover effects have only really shown to be influential when there is high spawning stock biomass and the eggs having to be deposited on suboptimal spawning habitat. For air temperature, for December and for March, both of these are density independent, and then I also have density independent December and March water temperature. So this is the full kind of kitchen sink model, but I examined 25 combinations of these climate variables with the stock recruitment model. And the way I compared them was looking at corrected Akaiki's information criteria, or AIC. And the use of AIC is looking at which of these models has the likelihood to best explain the data, and taking into account that there's a penalty for increasing the number of parameters. So just to kind of give you a basic framework for what this result slide is going to look like, the management unit is going to be listed here. The AIC comparison between the standard stock recruitment model and the stock recruitment models with the addition of variables that have been determined to be the best of those model combinations, and then which of the climate variables was related to the best model. And I'm going to, the numbers in the middle that are bolded are ones that are above 3, so, and that's an indication that there is a significant improvement of fit using the addition of whatever variable is indicated in the best model. So as you can see, there's a number of management units that have a significant difference between just the standard stock recruitment model and the model including a climate variable. And this is slightly updated since I presented last week at the modeling subcommittee, and that it turns out that water temperature, both in December for some months and March in others, seems to be the most influential factor. So to present this in a slightly different way, basically looking at the comparison between the standard stock recruitment model and the best model, the range between those values was 0, where the standard stock recruitment model was actually the best fit model, and 60. And that 10 of the 13 management units had AIC comparisons greater than 3. So that, again, indicates that there was an improvement of fit, including a climate variable in the modeling context. And that's all of the management units that are indicated in yellow are the ones that had AIC comparisons greater than 3. And again, as I mentioned earlier, water temperature comes out as the most influential variable. So December was the most important one for 5 management units, and March water temperature was for another 5. So just as a preliminary, very preliminary explanations of why those two could be potentially important indicators. If you think of increasing March or spring temperatures, that may very well be a result of increased zooplankton, or as a result of increased March or spring temperatures, that could lead to an increase in zooplankton production, and then a greater food resource for the larval fish, and hence greater survival. With December, there could be some relationship between storm events and egg mortality. So again, these are very preliminary potential explanations, and there are a lot of other considerations that I have to go into before I would make any sort of concrete conclusions. But one of definitely one of the factors I have to look at, and the next one I'm planning on looking at, is storms. And especially after both Mark and Jared's presentations with Cisco, it seems like a good direction to go with whitefish. So waves and wind is something I need to consider. I also want to consider looking at ice cover in a different context. Right now, I have just used the proportion of ice cover within each management unit, but it may be a more biologically relevant indicator to look at overlaying ice cover on spawning habitat itself. And if anyone has any leads on where to find digitized versions of spawning, like a spawning atlas for Lakes Michigan or Huron, if you could let me know. I have access to one for Superior, but at this point I haven't. I imagine someone must have those, but I don't have access to them yet. And then in terms of water temperature, I also am planning on looking at seasonal averages for the spring and the fall, and also looking at April as a potentially a better match for hatching for the spring temperatures. And then the same for air temperatures as well. And then lastly, once I've kind of compiled these climate variables, I plan to do a correlation matrix to make sure there's no collinearity in the variables that I'm using. So after kind of verifying that climate recruitment relationship, the next step is to look at projecting that in time with potential climate change. And there is a regional climate model that's being developed through the U.S. Geological Survey's Great Lakes Science Center and NOAA's Great Lakes Ecological Research Lab that is a dynamically downscaled model at the 40 km grid size, and currently there's a backcasting slice to 1970 and a forward casting slice to 2049 to 2079. And primary products of that model include both water column temperature and ice cover. And so in terms of implications for this model, we hope that it can inform harvest management for lake whitefish and potentially for the 2020 treaty renegotiation for the 1836 treaty waters. We hope that it can help suggest adaptive strategies for the lake whitefish fishery, potentially as a decision support tool. And then lastly, serve as a model for other fisheries impacted by climate change. And then just to go briefly into the next chapter for my dissertation, I'm looking at decision support. And in theory, decision support tools can aid decision making by systematically incorporating information, accounting for uncertainties, and also or facilitating evaluation of trade-offs between alternative choices. But in practice, if there's poor implementation of these decision support tools, it can either lead to indifference or even potentially opposition to the tool. So the idea with my next chapter is to look at investigating how can we improve implementation of decision support within a fisheries context. So to do this, I'm looking at investigating perceptions and recommendations for how to successfully develop a fisheries decision support tool. And to do that, and I have the pre-surveys with me today, I'm looking at distributing surveys on the future issues of lake whitefish management and decision support to both scientists, managers, and fishermen. And the idea is to solicit recommendations on how to implement the decision support tool and potentially how to apply that to my lake whitefish climate recruitment model. And so just with that, I have a number of acknowledgments, and I'll just kind of hand out the surveys, and if it's of interest to you, please consider filling one out, and I'll have a box at the end, or out on the back table in the back. So that's all I have.